perspective isn't being taken into account for curvature. It's really a globe killer, but the problem is most globe people don't have the ability to process that.
You've got to have some intelligence to work this out. If you don't understand it, that's fine. However, if you've got the intellect and you still disagree with this afterwards, then we have a big problem. And it's called...
Oh, what a day! What a lovely day!
Welcome to Flat Earth QED. I'm your host, Nathan Oakley, and joining me today is Anthony Riley and Chris Monk.
Okay, so it appears that on the Metabunk curve calculator, it appears that when we do the distance and the observer height, we get the value for the refracted hidden that everybody applies. The problem appears to be that they apply that value against the full height of the target that you're looking at. So, for example, a mountain at 1,000 feet, when it's 30 miles away, it's not actually 1,000 feet anymore. It has an apparent size reduction due to perspective, and we should apply the refracted hidden value against the reduced height because of perspective. Now, in essence, in a really concise sentence, if we live on a plane, things appear to get smaller over distance. But if we live on a ball, things get smaller over distance, but they also drop behind the curve. And because we're applying the refracted hidden value against the full height object, which is what every single baller ever does, it means that we're not accounting for perspective.
Right, so I mean, it's a really simple thing to set up. I was fortunate here and got some images from Paul on the plane, where he had done he had taken a drone up to an altitude of 1,950 feet and was looking at these three mountains in the United States: Mount Adams, which has its elevation 12,280 feet, and the other two here, Mount Rainier and Mount Hood, and their respective distances to them was, they're showing here 128 miles was the furthest mountain away from the drone at the time. And so this is an orthographic view of that model setup. So essentially on the bottom, you can see that it's basically the same type of model used on the curve calculator websites. Typically, you have a line of sight and the objects with their, well, they don't actually show objects, that's another issue, but they don't show objects on the curve calculators, but the hidden height would be represented by whatever's supposed to be behind this curve of the ball. So in orthographic view, you can see it's pretty simple. Straight line curve, objects in the distance to their locations, and a camera looking at them. Camera represents the observer's line of sight and the observer's altitude. Just to show you up here on the Z, the camera in this case is 1,950 feet. The ball that we're on is to scale, right, 7,916 miles, right, in diameter. And so it should be set up to scale. And when you flip from orthographic into perspective view through the camera in the top screen here, you see there's quite a change in what you see. And I'll zoom into the mountain in the middle here. So how this is set up is so that when you jump in the perspective view on the bottom, and see, I'll just view to that, so I can get in there a little closer so people can see it. So this orange line on the bottom represents where the camera is pointing. And it's going through basically the top of the mountain, right? And you can see that it'll pass through the mountain like so, and hit the target in the background on the picture to the pixels. So it's set up basically to hit it at the same point, and you can double check the angles and stuff. that way. So it's a straight line of sight over the curved surface. And when I rotate the camera, just to sweep through the picture, you can see it maintains a line of sight relative to this blue line on the top. So this would be like a level field of view. Where the blue line, that's what Paul was doing in his video, was showing that this is the, would be the horizon level line. And you can see that on a curved surface, comparing this mountain to this mountain, on a curved surface, this mountain is far too low on a curved surface compared to where it appears in the picture. You can see that it's the entire height of the mountain in reality is no longer where it should be. And the same applies to the other mountain on the other side. When I curve the camera and zoom back forth. So there's the one in the middle, the closest one. There's the one on the right. And it's a little closer than the one in the furthest away if we look at the numbers. Right, this one's at 123 miles versus 128 miles. And you can see when I zoom in here, it's a little closer to the target, right? There's still a discrepancy between the peak and where the mountain appears in the camera view versus the picture, right? So it's not as far off as the one to the left, the furthest one, because this one's 128 miles, right? What shows that there's in perspective view is an angular reduction just simply due to perspective, right? And once you apply that to the field of view and then curve it over the ball and put it on the surface, things would be exaggerated as far as how far away or how far they drop, right? It has to be considered in the diagrams compared to just an orthographic view, right? So if I go to orthographic view in the bottom again, just to make sure we're clear. This is an orthographic view, so you see that the picture is not being warped into any sort of perspective view. And if I toggle in and out of perspective, well, this is perspective. You see the vanishing point is now over here, and it's the other way, right? So perspective makes a big difference in what you see, right? If I just look at it on the side view again to be clear. You can see the blue line of sight is where the camera, a level camera, is looking over the curve. Oops. Let's go back to that view again. Keep on the right. Make sure we're there. So there's your drop between the three mountains. And I just averaged it in the view. So this is at 90 degrees. When the camera is at 90 degrees on the X, I can rotate it up and down, right? You can see that it changes the target. So it's basically, I averaged it to hit the top of this mountain to be as accurate as we can. But you'll see that there's definitely a curve drop, from the foreground mountain to the far field, like the near field versus far field, there's a change. And as you zoom in and out in the camera view, this is a good way to test that. If I go back to the right-hand view, zoom out a bit, and zoom up. Straighten that out, just a touch here on the Z. And if we zoom, this is basically at 35 millimeters, and if we zoom in and out, you can see that's what we're looking at right there. So hopefully that makes sense.
So back to the question on the Metabunk curve calculator. When they give us the refracted hidden value, does that mean that everybody is wrong to apply it against the target in this case, let's just say the mountain was 1,000 feet. Does that mean that we're wrong to apply it against the 1,000 feet mountain? Because the way I see it is 1,000 foot is different to 1,000 foot at 30 miles away. Correct?
Well, you'd have to do an angular size reduction of the target, a physical target, like a building or a mountain, at that distance first due to perspective, and then drop it on the ball model. Right. So
That
the
was my
angular
point.
size, the angular size would have to be put into the equation first, and then you take it in the drop value, and then calculate where you would see it appear. Right.
Yeah, that's my point. So basically, what's not happening on Metabunk is he's not addressing the perspective at all. He's just giving the line, the line that you've drawn from the observer out to the mountain. But because he's not put the mountain in, if you zoom in on that one that you're playing with there, Chris.
Well, yeah, I can kind of show you what they're like. People are confusing what's hidden. They're confusing the hidden value for a physical target. Right.
Yes.
It's two different things, right?
It's really a globe killer, but the problem is most globe people don't have the ability to process that.
And with that, I'm going to say first and foremost, a huge, massive, enormous thank you to Chris Monk for modelling all of those images, and a massive thank you to Paul on the plane for supplying them. Also a big thank you to Anthony Sleeping Warrior for joining us in this discussion. I've been Nathan Oakley, and I will see you all in the next video.
Oh, what a day! What a lovely day!